Apologize. All right. Yeah, I got 3 people here. I think that's pretty clear and easy to see. Oh, here's a 4th. Who is it? Twisson. Who can that be knocking at my door? Go. 7. Okay, so we're going to cover Faraday's law of induction and AC circuit. So I have a picture here of an AC circuit. For lab today, I didn't get a picture of an AC circuit there because we'll just move on. Yes, but for my presentation for lab. Okay, so picking up where we left off. Now you had a homework assignment, the one that was due on Friday, that had actually 4 calculus-based problems on it. And it did a variation on this, but I still want to go through it just so we have an official, a second official problem we've done with the Biot Savart Law. We already did one calculation with it, and here it's finding the magnetic field at some point P that is on the axis that goes through the center of a loop. So it's not at the center of the loop, but it's on the line that goes through that center. So this line is normal to the face or the area of the loop. And so if I want to find the magnetic field, the first question I always ask, and I got an email from, I don't know if all of you worked with Tori or if not, but Tori asked me some questions about this, and she went through this process to carefully identify which equation she should be using in each case. And the first thing to ask yourself is, do I have an exploitable symmetry for Ampere's law? If you don't, then you're going to have to go to Biot Savart. So we look at this and we have, a circle, we always think of that as nice symmetrically, but we don't have actually the exploitable symmetry where we can have our directions are just right, so it's parallel or perpendicular, or the magnetic field is going to be 0. We don't have those conditions, so that means Ampere's law is out and it has to be Biot Savart law. So then I've written the Biot Savart law, the 2 different ways I wrote it in class, one with R hat and one with R vector. And it just kind of depends on your preference. One problem might be more amenable to one equation, one to the other, but they mean the same thing. So I'm just going to choose the top one, where I'm going to have just R hat. First thing to do is to identify, okay, what is going to be my little piece ds? And so in this figure, they called it DL. You see the LI problem. But they just took a little piece of the circle here, and they said that's going to be ds. So instead of DL, we'll put ds vector there. It has direction. The direction is parallel to the direction that the current's going. And a magnitude of 1. So that's my ds. I have to have ds cross r hat. So if I do ds cross r hat, taking my right hand, putting my fingers in my right hand, that circle's supposed to be coming out toward you. So make my index finger come toward you, and then orient it so my fingers can bend toward the center. My thumb is pointing up at an angle. And so my direction is indicated with the right hand rule. What's the angle between ds and r vector? Between this ds vector and the r vector. The r vector is going from ds to my point P. What is that angle? 90. They're perpendicular. That makes me happy because the magnitude of ds cross r, I chose to use the bottom one, I guess. I was going to use the top one, but I accidentally chose the bottom one. So that's going to be r ds for the magnitude. And the direction we determine by using the right hand rule.
Now, if you had used the top one, wouldn't it amount to the same thing?
Yes, I just would have not had the r here on top, and I would have had r squared on bottom instead of r cubed on bottom. So it's going to come out to the same thing. Right, so it simply didn't matter which one I chose. Now I need my components. So I'm going to have the magnitude of dB, is equal to mu naught over 4 pi I r ds over r cubed. That's just substituting the r ds in for the cross product and just looking at the magnitude. And now we can see cancel out one of those r's. There's my magnitude. But I need to break it into components because it's a vector problem. So I'll have my dBx is equal to and dBy is equal to. So if I look at these, my dBx is going to be equal to dB, and notice that there is an angle that's defined in the problem. So I'm going to use that angle. That angle is this angle here. Right? We tend to think this angle, but no, it's the other one.
Which angle?
This angle right here, theta. Yeah, I'm gonna.
But is what? Is between R and R?
So it's the angle between the x-axis and dB.
Yeah, but what are you referencing? Because you have theta drawn somewhere else. You have theta drawn over between R and R.
I only see one theta. Oh, this theta here is the same angle.
Yeah, that's what I'm asking. But it's between what and what? The circle.
Well, here
R
it's between. It's
okay, so
between
R and R.
that.
Yeah.
Okay, I was only looking at the one they had printed. I'm sorry.
No.
Okay, so in terms of that angle, what portion of dB is in the x direction? Cosine theta. Cosine theta for the x direction. Right, I have this triangle, the adjacent side is. Okay, then we have, for the y direction, it's going to be, obviously, dB sine theta, the other one. And so, still no Sally. She's probably still sleeping, yeah. Probably won't wake her up. You can if you like. I'm not saying don't text her. I mean, better to learn than not learn. So now we have the x and y components, and now we just integrate each one. So we have bx is equal to the integral of dbx equals the integral of, let me put the non-variable stuff out front. Is r variable, yes or no? No, the r is going to be the same in all cases, so I can bring the r squared out here, and I just have, well, what about the cosine, or the theta? Is theta a variable? No, it's going to remain constant throughout. So I can bring the cosine theta out as well, and then I'm just left with integral of ds. I'm going around a circle, so that's going to be from 0 to 2 pi. Capital R was the radius of the circle. That's a pretty simple integral. Agreed? So that's what I get for my x component. I think I did all that right. What about the y component?
Oh, I see. Can you scroll down just a little bit? It would be the same thing as sine theta, wouldn't it?
It's not. The x direction stays the same as I go around the circle. The y direction is going to be rotating around in a circle. Right? if I move down to here, if I take this piece, then the y component is going to be coming 90 degrees to what the y component was there. Right? That's why they called it perpendicular in there. They didn't put y, they put perpendicular. Because it's actually going to be changing between the y and z directions. But we can use symmetry arguments to make our lives simple. If something is constant and goes like this around a circle, what does it add up to? 0. So my integral of dby equals 0 by symmetry. So all I have is the x component, which is this. Now you look at it and it really has two variables. It has the r squared and it has the cosine theta. So let's figure out how we can combine those. The cosine theta is the one I want to get rid of. So how can I replace cosine theta? Go ahead. If this is theta, then what is cosine theta? Right. So I can put into here, this is equal to, notice 2 and 4 will give me on bottom of 2. Pi and pi will cancel. So I have this relationship. Ah, the good times, the good times. This is a correct answer. I'm done except for one thing. We usually want it in terms of x, how far away we are, and capital R, the radius, not r. And so I will actually replace r with the square root of x squared plus capital R squared. And so I get bx I get that relationship. So, yeah. That is the correct relationship. That's the magnetic field. What's the case that you had in your homework? How does this compare to what you had in your homework? I think you had at the center of a circle, didn't you? I thought you did. Well, even if we didn't, for the one with the proton, it asks us to find the magnetic field at the center. We use the equation for the magnetic field at the center of a circle with a current. So if you're at the center of the circle, x equals 0, so bx is equal to mu naught I r squared over 2 r cubed, or mu naught I over 2r. And thus the answer to the question, why was the equation for the magnetic field created by a single wire mu naught I over 2 pi r, but for a loop it was mu naught I over 2r? Why no pi? Came out from very different calculations. Put center. Yeah, that's very, very nice. Very nice. They came from different calculations, very completely different calculations. I mean, one was using Ampere's law, although we did it both ways. One was using the Biot Savart Law. And, of course, the distance from the wire was different for every piece of the wire. For the loop, it was the same distance for all pieces. So you can see there's quite a bit of difference. It's just the equations are so similar that you ask, why does one have a pi and one doesn't? Okay, so any questions about the application of the Biot Savart Law?
Can you just go back up just for a second?
I can. How high?
Just the picture. So is this, the idea is there's a wire running through the middle of the loop?
No,
It's just a loop
there's just a loop, and we're finding the magnetic field created by current in that loop.
at some random point.
Yes. Along a line that goes through the center of the loop.
Okay, so that's kind of our reference point, is the line going through
Yeah.
the center. So that's why dB parallel and dB perpendicular. dBx is basically dB parallel, right? So
Well, you can define an x, y, and z axis, and it's parallel to the x-axis, so that's why it's dBx. But the one that's dB perpendicular is actually changing between the y and z axes as you go around the circle. Yeah.
So why did they, I guess the part I'm a little bit confused on is why they had DB drawn in as they had it? Because, yeah, or like if we.
I don't understand the question.
I see that they have, where they have DB drawn in, and I see
Yeah.
from, if we look at the little DB that they have drawn in, how we would have the, cosine and sine relationships
Mhm.
from that.
Mhm.
But if we don't already have that, like, how would we know to draw that
Okay.
like that?
The first thing we did when we did this cross product was we did the right-hand rule and found the direction. And so this dB is the direction that we found from application of the right-hand rule.
Okay, thank you, that makes sense.
So,
So it had to be perpendicular to the r vector and perpendicular to the s vector. And so that specified exactly what the angle was. Question, Chad?
so the whole dB equal to mu r over 4 pi times IDS cross r of r squared, that whole thing comes from the Biot Savart Law.
That is the Biot Savart Law.
Right. So that'll just be given to us.
The Biot Savart Law, yes. Yeah, not something you have to memorize. And Ampere's law. Now, I was talking about Tori's question and, choosing which one. Another thing was, like in one of the questions it says, what is the correct equation for dB? Well, Ampere's law doesn't have dB in it. It has the integral of B dot dA, or B dot dL, excuse me. It's Gauss's law that has the dot dAs.
Can you write Ampere's law if I that's safe, right?
Yeah.
Is it, I'm just looking online right now.
The integral of B dot dL is equal to mu naught times the current enclosed. It's a very simple looking law. And it's not that hard to apply if you have a symmetry that's easy.
And it won't work here because
It won't work here because we don't have a symmetry that's easy. Like what shape would I make that's going to have a good symmetry so each part of the wire's magnetic field is simple for me to calculate?
a line going through the middle of the loop wouldn't do that?
Well, a line going through the middle, a line going like this forever, it goes on forever. I suppose I could then go, once I get out to forever, the magnetic field is 0 and go all the way up and come all the way back. But I have then an integral over this entire line. I don't have the magnetic field at a specific point on the line.
Oh, so this is for a specific.
What if we had if we had an infinite wire and that's what was generating the magnetic field, and
Yeah.
kind of at some point other than that, then that's what we're using, right?
Yeah, then Ampere's law is very simple. And like we saw when we did the solenoid, we did use the going out to infinity, but it was 0 everywhere except for in the center where it was constant. And so we were able to find the value there where it was constant. With the example of having a straight line that goes out forever and then doing a loop that stays infinitely far away, it's varying along that straight line. I can't find it at a point still. Okay, so that ends our Biot Savart law. Now let's talk about AC circuits. So I'll start with just a very simple, with a resistor, we have a simple relationship between voltage and current, V equals IR. What did I do here that's different than what you've seen? I just made it very clear that I can have a current that varies with time, and that will cause a voltage that varies with time. And so at any instant, the voltage is equal to the current at that instant times resistance for a resistor. And of course, on the top, we have the symbol for a resistor. In an AC circuit, that's just the same. There's no difference. There's no added complexity whatsoever. Move on. A capacitor. A capacitor, we've learned, it has the charge separation is equal to the voltage difference between the two plates times C. Now I say the charge separation, that means I took charge from the top, moved to the bottom. So the top is like plus Q and the bottom is minus Q. We just use Q for that. So that looks fine, but of course that doesn't have current in it. It's not relating voltage and current. It's relating charge and voltage. But if we take this equation and take the derivative of both sides with respect to time, the left side is dq dt. But dq dt is defined as current. So for a capacitor, the current at any time is equal to the capacitance multiplied by the derivative of the voltage with respect to time. So what does this mean? This means that the current is proportional to the rate and change for the voltage. It actually makes great sense. Why does it make great sense? Because what's going to charge the capacitor? Not specifically voltage. I have to have charge moving on to the capacitor to charge it, or charge leaving the capacitor to discharge it. And current is the rate at which that's occurring. And so, if the current is larger, then the voltage should be changing faster, because you have more charge per second arriving. Right? It makes perfect sense. Now, there's some important things about capacitors I want to point out right now. I have two plates. How much charge passes between the plates if we don't do something damaging to the capacitor? None. And yet I talked about the current for the capacitor. Wouldn't by definition the current for the capacitor be zero? Since there is by definition no charge passing between these two plates? I would think so too. This current is technically the current coming to the capacitor or leaving the capacitor, not the current between the plates. The current between the plates is going to remain zero. But you have, on the bottom you have charge going this way into it, on the top you have charge going this way out of it. The current is the same on both sides of the capacitor. And the capacitor is storing not charge, but storing a charge separation. And so, yes, technically there's no current between the plates, but there's current coming to one side and leaving the other side. And we just say, okay, it's the current of the capacitor, there's the current coming in one side and leaving the other side. And we just don't worry about the fact that there's no current between the plates.
Ever? Or is that...
Well, ever unless you get such a big voltage that you have an arc that passes between the plates. That's why you have the maximum voltage listed for a capacitor. Go with that voltage and you'll have actually an arc pass between the plates. Then you'll have current between the plates and probably damage your capacitor at the same time. So you're not supposed to go over that voltage because you're not supposed to have any current between those plates.
I guess that kind of confuses me, because then how does charge, isn't charge passing between the plates though? I mean, it isn't.
Charge is moving to, right, I have, let's say current is going like this. What that means is that I have electrons. Electrons are coming here and making this side negative. And electrons are leaving here, making this side positive. But there's nothing actually passing between those two plates.
Wouldn't everything kind of come to a halt at some point?
Yes, at some point it should come to a halt. Unless I do something like use an AC circuit where I just keep changing things back and forth.
So you're saying, so that's at the point at which it's charged?
Yeah, if you do a DC circuit, if you just do the transient like we've already studied, you put this voltage with the resistance, and the charge flows until you finally reach a steady state, and there's no more current anymore, because you've reached the balance.
And then when you go to discharge it, it just reverses the flow?
Yeah, yeah.
Gotcha.
But with an AC, you're constantly charging, discharging, and you don't have the balance reached. So this is an important equation to describe what's going to happen in an AC case for a capacitor. Note that your current is C dV dt. That is, it relates to how quickly the voltage is changing. So on the capacitor, you cannot have your charge go from 0 to 10 coulombs in no time. It takes time for that charge to jump, right? And that means it's going to take time for the voltage to rise. So you can't have a discontinuous jump in voltage. The voltage always has to be continuous in a capacitor, which makes perfect sense because if the voltage was discontinuous, what would dV dt be? If voltage goes from 0 to 10 volts at an instant, what would dV dt be? Undefined, which means your current would be undefined. Instead of having a finite current, you'd have a current that's gone approaching infinity, or undefined. So you have to have a continuous voltage in a capacitor so that your current stays defined. So here's an example for a circuit that has a resistor, a capacitor, and a power supply. Now I put in here that my power supply is making a constant current. Why did I put the current in? Well, because the current is the same for both the resistor and the capacitor. Why is it the same for both? They are in series. So since they're in series, they have the same current everywhere. And so I have I resistor is equal to V resistor over R is equal to I capacitor, which is C dV capacitor dt. Make sense? They have to have the same current. So I have this relationship. But VR and VC are related by the fact that V source minus VR minus VC has to be 0. What do we call that equation? An application of Kirchhoff's voltage law. I went around the loop. I went up V source, down VR, down VC. Now I have the slide after this is actually the sign convention. I should have put it before. I think it's the slide after this. Oh, it's the slide after this. So I have this relationship. So let me say, let us just say that VR is equal to V source minus V capacitor. That's just taking the equation above, taking this equation and solving for VR. And then I'm going to put that VR into this equation. So I'm going to have V source minus VC all over R is equal to C dVC dt. I have two variables here. What can I do? What are the two variables? One of them should be VC. And the other one is, actually, you know what? I'm doing it this way for the integral. Let me do it so I do a derivative. Doing a derivative is going to be easier than an integral, right? How can I do this differently to make it so I do a derivative? I'll just solve this equation for VC. Right, if I solve this equation for VC and make that substitution, I get an equation that is going to be simpler mathematically for us. I'll have VR over R is equal to C d dt of Vs minus VR. And so if I just take those derivatives, my VR, did I write it anywhere? I didn't. VR is equal to, actually, you know what, this turns out it's not easier. VR is equal to IR. And so if I do the derivative of VR, I'm going to have that equation. And doing the derivative of the VR is really quite simple. Right, derivative of sine is, and you have to bring out the omega. So I'm going to have, for VR here, what's VR divided by R? By definition, it's going to be the current. So I'm going to have, let me change colors. I max sine of omega t equals C d voltage source dt, because I don't have a function for a d voltage source, minus omega C.
My max sine omega t is just given.
I gave that right here. And so now I have an equation that is relating my my voltage and current in a most disconcerting fashion. This is not the way I intended to go through this problem. Maybe I should have stuck with my original. But you can see that we have a cosine omega t here and a sine omega t here. And so I would have, solving for dvs dt, I have to divide everything by c.
What is dvs dt? Like what quantity is it representing? It's not
What is what?
velocity.
The source. That's the voltage of the source. Sorry.
Okay, so dvs dt works out to be the voltage.
Whoops.
The total voltage.
I factored out something I couldn't factor out. The only thing I can factor out is the I max. So that's what my voltage for the source would have to be, the derivative of it. And now I have my variables separated.
Divided by c.
Okay, I divided by C. This here is supposed to have been the C.
Okay, that's what I was wondering. Why?
Yeah, I divided correctly by C here,
Yeah, I see.
but I did not on the first term. Okay, so now we could integrate that up, and we had the voltage for the source would be equal to I max. Integral of sine omega t is derivative of sine is positive, so integral is negative. So I get back to this. It was kind of a circuitous route. I should have stuck with my gut feeling that I started with. But what we have is the voltage source is equal to, and if you separate the pieces out, you will see that maybe I shouldn't have added an extra page. This and this combines to give me V sub R. So these things here this must be the voltage across the capacitor. So we have minus I max, and instead of a sine omega t, it's a cosine omega t. So it's 90 degrees out of phase. And it's I max over omega c. So we have, come on, change for me. The voltage across the resistor was I max times R times sine of omega t. The voltage across the capacitor was I max over omega c with a minus sign out front, cosine of omega t. If I plot these, and Sally and X goes 0 to, go out to 9 again. Sally and Chad saw me do this earlier to the best of my abilities. If I plot these out, I will find that the voltage for the resistor should look something like missed. Hit there. That's what the voltage across the resistor looks like. And the voltage across the capacitor, because of that phase difference, the phase difference being this being a cosine minus cosine, it starts, negative cosine means it's going to be a negative value, and it's going to go like that. So the capacitor voltage has its peak, has its peak, it's supposed to be right there for the peak, shifted from the peak time for the voltage across the resistor by a factor of 1/4 of a cycle. Quarter of a cycle is 90 degrees if you're using degrees, or pi over 2 radians. And so because of this, we say that the capacitor voltage lags, that's an LAG, it's very not, come on. Did I not close that? By 90 degrees. Lags because this is a later time. The x-axis here was time. The y-axis was voltage. And so it's a later time when you reach the peak for the capacitor. How many people had already learned that? Uh-oh. Just for me. I expected my engineering students to raise their hands. Yeah. In like engineering electronics class. Okay, so yeah, it's a basic thing that the voltage is going to lag by 9 degrees. Now we have a mnemonic that I'll introduce after we do the inductor to help us remember that. So let's go to the inductor. Oh yeah, it's the inductor that I have the slide for the direction, the sign convention. For an inductor, we have Faraday's law of induction. Faraday's law said that the EMF induced was equal to minus N, we're in calculus class, derivative magnetic flux with respect to time. And so the magnetic flux is going to be B dot A, or B times A times cosine of the angle between the two. So here I simply replaced the magnetic flux with BA cosine of theta. So that's just Faraday's law of induction. And in fact, this first line is Faraday's law of induction. I forgot that that's exactly what I wrote for the first line. So Faraday's law of induction tells us about an EMF that's induced by having a changing magnetic field. Well, an inductor is a self-inductor. More specifically, an inductor is going to be created by having just a coil of wires. And so if you put a current through here, that current creates a magnetic field. So the current creates a magnetic field that's going to be B is equal to mu aught number of turns per centimeter I, or
Number of turns per centimeter? Is that
not per centimeter, per meter. Number of turns per meter, yes. Or mu aught N over Li. So that tells us what the magnetic field will be created, that will be created inside of a coil. Now, what would happen if I replaced the air inside a coil by, let's say, iron?
Wait, what?
If I replaced the air by iron, remember I had the little ring tosser here? When I put the iron in the coil, what happened? It got stronger. And in fact, it got stronger because this mu aught just became mu for whatever the material was. So if I take away the aughts, that allows me to say, okay, for whatever material I have inside of the coil. So you don't have to make an air coil. Usually you don't make an air coil. There are some problems, though, if you don't make it an air coil. Because what's going on when you put that core in the coil and it amplifies your magnetic field? What had to happen for it to amplify the magnetic field? The domains had to align. If you take something that's like this and you move it to this, that required you to do some work. So there was some energy involved, which means that you lose a little bit of energy because of that orientation change. Also, it takes some time for that to happen. And so by introducing something other than air, you introduce some energy loss. A capacitor stores energy, right? And it gives it back. An inductor is supposed to store energy in a magnetic field and give it back. But if you have some work involved, that means you're going to lose a little energy. Well, what did we call the devices where I push charge through and I lose energy? Resistors. So we have an effective resistance for an inductor that's based on how much work is going to be required to align the little domains.
I'm confused. So as in any given inductor is always going to have something introduced in?
Okay, an inductor, if you just take an inductor and you measure the resistance across the inductor, you'll get close to zero. And you get close to zero because it's just wire wrapped in a loop. And the resistance of the wire is very low. But when you put that in a circuit that is an AC circuit, and you're constantly changing the magnetic domains, you're constantly doing work to change those domains, and so you have energy loss that looks like a resistive loss.
Because of the change in direction of the current.
And it's occurring because of the changing direction of the current, yes.
Oh, okay. So you were talking about something else when you were talking about like putting something other than air in there.
Well, in real life, we do put something other than air in there, but that introduces a non-ideal behavior. So my equations here are working out the ideal behavior. And I say, well, in real life, there's a little non-ideal that you have to deal with. Okay, continuing on. So the magnetic field is given by, and you'll notice I used this equation to substitute for the magnetic field. the angle, if I just have this coil, the induced magnetic field is going to be in this direction, which is the same direction as the area. So B dot A, the angle between them is 0, cosine of 0 is 1. And so I just put cosine of 0 here, which has a value of 1. So I'm going to drop it off in the next part of the equation. When you put this all together, the only thing that's varying is the current, so I have this constant part times the rate at which the current changes. And so we just define this constant part as the inductance. So the inductance is relating the voltage difference across a coil of wires to the rate at which current is changing. If the current was constant, what would the voltage difference be across a coil of wires with zero resistance? 0. Because if it was DC, you would just have V equals IR. But because you have the coil of wires, that coil of wires is going to then, when current flows through it, creates a magnetic field, and there's energy that went to that magnetic field. And so you have energy that moved from your current into stored in the magnetic field. But then it will return that energy if you stop forcing current. Lenz's law says that it's going to create a current to try to maintain the magnetic field. And so it's going to push current to try to maintain the magnetic field until the magnetic field is gone. So it stores energy in the magnetic field and then it returns it. So that's the function, and this equation, this equation right here with L equals mu naught n squared A over the length is the inductance. So it's a physical equation, just like a capacitor had a physical capacitance equation. We have a physical inductance equation that has to do with this here is the material that you've wrapped your wires around. N is the number of wraps you made. A is the area of your loops. And L is the length of your inductor. Now, does anybody notice a mathematical error on my page? It's there intentionally, by the way. I dropped the negative. What did I say in class that negative was there for? Remind us that we need to pay attention to Lenz's law for the directions. So this is where I have my direction convention. And you'll see this slide again in lab today. The direction convention is that if you have increasing current, your plus and minus compared to the current direction is the same as it is for a resistor. So we dropped off that minus sign, and it gives us this current convention, which matches pretty well. Now, if the current is decreasing, that means di dt is negative, and so that's why it flips if the current is decreasing. So when you draw a circuit, you just use this for your circuit convention for signs. So if I draw my circuit and I have an AC source, and I say, okay, so here's my resistor, and here's my inductor, and here's my capacitor. In all cases, if I assume current like that, then this is going to be plus minus, plus minus, plus minus. So I have the same convention as I used with the resistor for inductors and capacitors.
So I don't understand why the sign matters at all then.
Well, it matters because when you use things like Kirchhoff's voltage law, if your signs are opposite, you get a different equation.
No, but I mean like in your equation, if you said we always set it up like that anyway.
Well, we have to have a sign convention to make it so we can always set it up like that. If we'd chosen a different sign convention, then we would have had to change the picture. We would have had, if we had chosen the opposite sign convention, if I hadn't dropped out that minus sign, then it would have gone like this. And that makes a difference of a plus sign or a minus sign.
So when we're doing the equation, the minus sign indicates. So if there was no minus sign in that equation, then we should write it the other way. Right.
Let me just go back. This minus sign that I circled was dropped for the specific reason so I can have this sign convention. If we had left it in there, we would have had the opposite sign convention. And then I would have had to use a different rule for how I define the positive and negative side for an inductor than I use for a resistor.
Right, but I'm saying, like, if you worked out your equation and it came out positive, not negative, then you'd have to switch that.
Well, it couldn't, but...
Oh, I see.
Okay, so this is the equation that relates voltage and current for an inductor. Now, I talked about the voltage and current relation for a capacitor, and we saw that you cannot have a discontinuous jump in which variable for a capacitor? Voltage. Why was that? Yeah, you can't magically have charge appear. Now, with the inductor, we're building a magnetic field, and we don't have particles of magnetic field that are being stored. So we can't see it the same way. But mathematically, I looked at and I said, well, we had the derivative of voltage. If we had discontinuous change in voltage, that derivative would have been infinite or undefined. And so that wasn't possible. Now, if you look at this equation, using that same logic, what can we not have a discontinuous change in? Okay, so current must be continuous. Now, I am out of time, so I will finish by pointing out something that the people in the electronics class have learned. When you have inductors in a circuit and you have a switch, you tend to have bouncing when you close the switch or open the switch, because the inductor is going to try to force current, and all of a sudden you've broken the path, and so the current can't go anywhere, and the inductor kind of freaks out. And so you have very rapid fluctuations because of that action. And so if you have an inductive circuit, they often employ what we call make-before-break circuits, where you connect to somewhere else before you disconnect the original one so that you remove that bouncing signal. All right, I'll see y'all at lab time.